Good morning, everyone. Before we begin, I'd like to thank Oscar Grunwald for bringing together this international conference, and Bruce Lundgren for chairing the session and his kind introduction. The title of my talk, as you can see, is Does God Gamble with Creation? And of course the title references Einstein's famous statement that God does not throw dice, a statement made with reference to quantum theory and his belief that quantum theory was not ultimately random, not ontologically random, but ultimately deterministic. I've argued in my paper Evolution, Mind, or Randomness that the laws of nature are God's providential intentions for matter. If physics is fundamentally random, then science and theology are in conflict. A projection is a diminished mapping, that is to say, if we take three-dimensional world and we map it into a two-dimensional picture, then we have lost dimensionality and we've lost information. For example, if we have a house plan, the plan can be true, but it doesn't include every bit of information about the house. The plan is two-dimensional, the house is three-dimensional, and of course the house has a lot more information than we can put down on a piece of paper. So, in the projection paradigm, we have reality, and in this case we have physics looking at it from one direction and theology looking at it from a different direction, but there's still one reality, and so even though they see different things, what they see cannot ultimately be in conflict. So the theological projection focuses on God in relationship to us. Its basis is faith and reason, and as Augustine said, it's faith-seeking understanding. Its method, I would suggest, is interpretive. It reflects cultural context, because we're trying to interpret our faith in terms of our cultural context, and of course that context includes science. The criterion of acceptance in theology is worthiness of belief. And worthiness of belief has two aspects. One is intrinsic, that we want our beliefs to be resonant. So, for example, when I hear that God is love, that resonates within me, and I'm inclined to believe it. And the other is extrinsic. We want our beliefs to be consilient. That is to say, we want them to dovetail with the other things that we believe and know about the world. And so, if science changes our perception of the world, then our theology has got to reflect that. So, for example, we had Catholic theology, which is my tradition, holding a majority view for hundreds of years that Genesis was to be taken literally, but a minority of theologians said no, it's figurative. Then, in the late 19th century, when geologists showed that the Earth was much older than would be allowed by a literal interpretation of Genesis, Catholic theology shifted gears and made the minority position, namely that Genesis is not to be taken literally but figuratively, and made that the majority position. So theology does respond to science. The physical projection is, of course, different from the theological projection. Its focus is on measurable events, and because it's focused on measurable events, it ignores the knowing subject. We don't care about the interior state of Ptolemy or Galileo or Hubble when they're observing the stars. We only care about the observations they made, their measurements and data. And it ignores immeasurable objects because they simply fall outside of its method. And of course that includes theological objects such as the soul and God and so on. That does not mean that it's rejecting the soul or God, it just means that they fall outside of its scope of interest. The basis of the physical projection then is observation and modeling, and its method is hypothetico-deductive, which means that we frame hypotheses, we deduce conclusions, and then we compare them to our observations and experiments to see whether the hypothesis holds up. And the criterion of acceptance is explanatory power. We accept a hypothesis if it's parsimonious, that is to say, if it doesn't have a lot of extraneous assumptions, and if it has an extensive scope of application. So if with a few assumptions we can explain a great many observations, then we're inclined to accept the hypothesis. So now I'm going to turn to physics. Some Christians might argue that theology, as the queen of the sciences, ought to trump the other sciences. Certainly naturalists would argue that theology is no longer the queen of the sciences, but that physics is, and that it ought to trump theology. My own view, based on my projection paradigm, is that each is seeing a different thing, and because each is seeing a different thing, we have to respect the methods of each science. And so if we're going to resolve the claim that quantum physics is incompatible with divine providence, then we have to examine the physics using the methods of physics and not the methods of theology. So what does physics tell us? Well, I'm going to just rely on textbook physics, and I'm not going to rely on any particular interpretation. And what textbooks teach us is that if we have a system, a quantum system, and we don't observe it, then it's deterministic. So, for example, here we have a little system with some atom, let's say, that's going to decay. We have a detector, we have a readout, we have an observer, and an event occurs which we measure, and while this system is deterministic, because we've stuck our finger in there and diddled with it by measuring it, there's a random element, and that randomness is essentially where quantum randomness lies. Quantum theory does not say that the system with its decaying particle is ontologically random. It says that it's completely deterministic, but what is random is the observation process. But now let's consider another observer, and because systems are essentially subjective, a system is what I decide a system is. It has to have some sort of intrinsic unity, but basically I can draw a box around anything with some intrinsic unity and say that that's the system. So this second observer is going to take the entirety of the first system and its observer and observation process as a system that he's considering, and if this second observer does not observe this, then system 2 is deterministic, which means that the observation, which appears to be random, is in fact deterministic. So how can we explain random measurements given the fact that physics teaches us that they are in fact deterministic? Well, the standard approach has been the hidden variables hypothesis. It's also called local realism, and it's based on two principles, namely locality, that things cannot act where they don't exist, which seems pretty self-evident, and realism, and here realism has a special and particular meaning, namely that a system has pre-existing values for any possible measurement. I would suggest that this is not realism at all, but Platonism. So this combination, namely locality and realism as it's defined here, is ruled out, first of all, theoretically by Bell's theorem, and to some degree experimentally by Bell's inequality and Aspect type experiments. However, when you look at the experiments, you find that they're not all that conclusive. They have so-called loopholes, which are not loopholes at all, but mathematical properties which are required, which the experiments do not in fact meet. However, Bell's theorem is based on accepted quantum mechanics, and so we can say that the hidden variables hypothesis is ruled out theoretically unless either locality or this particular form of realism is not true. So let me suggest that the problem with realism as it's been defined here and why it is Platonism is that quantities are measurable, not pre-valued. If you'll recall, Plato insisted that the world was made of numbers and figures, so that numbers pre-exist in external reality. When Aristotle criticized him, he pointed out that values result from measuring and counting operations. And so quantities in nature are measurable or countable, but they are not, in fact, already numbers. And this is the view that has been taken by 20th century physics and continues today, namely that the values that we have depend on the operations that we use in obtaining them. So, for example, length and mass and speed are all relative to our frame of reference, and we will get different answers for them if we measure them in different frames of reference. In the same way, position and momentum and spin in quantum theory depend on the measuring process that we choose, and so there's no reason to think that they have pre-existing values. So measured values reflect the interaction of our system and detectors, not prior values. So now let's look at the so-called EPRB experiment, the Einstein-Podolsky-Rosen-Bohm experiment. In it, we have a particle with spin 0. This is a thought experiment. And there are two detectors. The particle is going to decay into two spin 1/2 particles. And we've set up the detectors to measure the spin along different axes. So in this particular example, the one on the left is measuring along the front and back axis, and the one on the right is measuring on the up and down axis. And whatever orientation we put our detector in, that forces the measurement to be along the corresponding axis. So we can vary the direction or the orientation of the various detectors, and the correlation between our measurements turns out to be unexplainable on the basis of a pre-existing value, unless there is some sort of magical communication between the detectors on the right and left, which is called spooky action at a distance, and it violates the common sense principle of locality that things only act where they are. So here we have our event. The particle in the middle has decayed, and as a result, two spin 1/2 particles come out. They have equal and opposite spins because the spins have to add to 0, the initial spin. That's a consequence of the law of conservation of angular momentum. And Bell's theorem implies that the measured spins are unexplainable by any choice of pre-existing spins if locality holds. So now let's suppose that we've finished our measurement, and on the left we found that the spin is oriented toward the front, and on the right it's oriented up. And then we look at the measured results, and we see them down here on these two vectors. And their sum, when we add the two vectors head to tail, which is what you do if you'll remember from your high school physics, is this red vector, which is not 0. Now, that is a violation of conservation of angular momentum if we assume that the measured values are the pre-existing values. So where does the extra spin come from? Let's step back and think about how it is that we see reality. What are we experiencing when we see reality? Let me suggest that we're not experiencing the reality we're looking at alone, but we're experiencing two objects, namely the world, which I'm calling the objective object, the thing that we think we're looking at, and also human sentient powers, which are the subjective object. And those two together are the total experienced object. So, for example, when I look at the world, I realize, if I think about it, that I have the power to see, I have awareness that I can see blue, and so on and so forth. So my experience has a lot of information about myself, which I simply normally don't think about, but it's there. And so by focusing on the objective object, we leave a lot of data, a lot of information on the table. In the same way, when we're measuring spin, and we ask what we're experiencing two objects, namely the particle measured, which is, let's call it the objective object, the thing that we want to be looking at, and then the detector. And the detector essentially plays the role of the subjective object. We don't think about it, but there's information in the total experienced object about the detector as well as the particle. So the answer to our question is that the extra angular momentum comes from the detector, and so what we're detecting is not the state of the particle prior to its interaction with the detector, but the results of an interaction. So now we're going to look at the physics that describes the particle, and this is standard physics. I'm not just making up something for my interpretation. Detectors are made of bulk matter, and so we need to ask ourselves, what does physics tell us about what happens when an electron enters bulk matter? Well, the standard approximation for dealing with bulk matter is the Hartree-Fock approximation for many electron systems, which is shown here. The first term is the term that you would normally find for a free electron. Electrons traveling through space, not interacting with anything, are described by this first term. These additional terms come into play when an electron enters a region where there are atoms with nuclei and other electrons. This term represents the interaction of the electron with the atomic nuclei, and these terms represent the interaction between the electron and other electrons in the detector. Now, to calculate these terms, you need to know the initial state of each electron in the detector, and there's about 10 to the 23rd or more of these. 10 to the 23rd is a 1 followed by 23 zeros, so there's a lot of electrons here, and we know virtually nothing about their detailed states. Let me suggest that all we need to explain the randomness of our measurements is our ignorance of these 10 to the 23rd or so electron states. Their states are manifest variables, not hidden variables. We know that they exist, we don't have to make them up, and they're all that we need. There's something else very interesting about these terms. They explain why the wave function collapses when we have a detection event. Now, the thing to notice about these terms is, in the interaction terms, there are additional powers of psi in the equation, and these additional powers cause this particular equation to be nonlinear. Nonlinear means that you can't add two solutions together to get a third solution, as is supposed by the so-called Schrodinger's cat thought experiment. Here, the experiment supposes that we can add a live cat and a dead cat and get some sort of superimposed cat, and a broken bottle of cyanide and an unbroken bottle of cyanide and a raised hammer and a fallen hammer, and that all of these things are physically possible. But because the Hartree-Fock approximation is nonlinear, it doesn't accept superposition. Superposition is then physically impossible, and so is Schrodinger's cat. So, my solution is to replace hidden variables with manifest variables. Manifest variables are variables that we very well know about. We know that there are electrons in our detectors, and that those electrons interact with the electron that we've sent at the detector. We further know that these manifest variables, namely the state of the electrons in the detector, are unknown to us. And so we don't need to have a hidden variable in the system that we're looking at in order to explain randomness. We just need to have the manifest variables that are unknown in the detector. However, the fact that we have the detectors on the right and on the left correlated indicates that the detectors are entangled. Now, entanglement means that once objects interact, they share information, and this is an accepted principle of quantum theory. Now, for this reason, the detectors are kept separate. However, light travels at 186,000 miles per second, 300,000 kilometers per second, and so within less than a second, anything that is on Earth is going to be able to interact with anything else that's on Earth. So even though the detectors are kept separate, there's no guarantee that they can't be continually interacting with each other. Furthermore, all matter shares a common origin in the Big Bang. So, from the common origin of all matter has got to be quantumly entangled. So the matter that makes up the detectors has been entangled or correlated literally since the beginning of time. So, in sum, problems that we have with physics must be resolved using physics. Unobserved systems, including systems with observations, are deterministic. This is told to us by standard textbook physics. Measured values are not pre-existing values. We know that because if they were, conservation of angular momentum would be violated. And so quantum randomness reflects ignorance, not God playing dice. So, if the world is deterministic, what about free will? Determinism is true means that purely physical events are immanent in prior states. So if we know the initial state and we apply the laws of nature, we're going to get a well-defined final state. That seems to leave no room for free will, because free will says that we are the radical origin of new lines of action. If everything is immanent in the world before I was born, if all my actions were there ready to be played out by simply following the laws of nature, then I would not be responsible for anything. And free will, at its core, is a concept of human responsibility, that we are responsible for at least some of our acts. I would suggest that physics is only one projection of reality. And because it's only one projection of reality, it has nothing to say about subjective objects. Remember that the interior state of Ptolemy and Galileo and Hubble was not of interest to physics, and so information about it was excluded in the initial abstraction that physicists used to begin their science. And because we have no data about the subject, the knowing subject, the willing subject in physics, physics has absolutely nothing to say about subjective objects. It's beyond its scope of competence. Thank you very much.